Section 7.7, Inverse Relations and Functions. Our objective is to find the inverse of a relation or function. Recall that a function means for every input we have exactly one output value. So from a table, remember we look for the repeating x values, or we can do the vertical line test. Now we're going to talk about inverse relations. If a relation maps an element of A of its domain to element B if its range, and remember domain is your x values, range is your y values, then the inverse relation undoes the relation and maps B back onto A. So what does that mean? It means if A comma B is an ordered pair in the relation, then B comma A is an ordered pair in the inverse relation. To find the inverse of a relation from a table, you're going to switch the x and the y values. To find the inverse of relation from an equation form, we're going to switch our x and y values, and then you're going to solve the resulting equation for y. So these are the steps that we follow given a table or given an equation. So the first example that we're going to look at is to find the inverse of a relation M, graph the relation, and then we're going to graph its inverse in the same coordinate plane. So for this, if I want to graph this relation, I'm just graphing the set of ordered pairs. So I have -1, -2, 0, -1, 1, -1, and 2, -2. So this right here would be my relation. And remember, we do not connect the points because these are discrete values. We weren't given an equation, so since we weren't given an equation, we don't connect the points. Now for this, if I look, I'm going to look to see if this is a function or not, even though the question didn't ask me to. I know this is a function because I don't have any repeating x values, so for every input there's only one output. And remember, we can also use the vertical line test to determine whether or not something is going to be a function. So here, if you look, as I go through with my vertical line, it only hits in one spot on my vertical line for each of the points. So therefore, it does pass the vertical line test, and this would be a function if you recall from earlier in the year. Also, let's just go ahead and write down what the domain is. Remember that your domain, and I'm going to use D for that, is all your x values that we have, and then you write them in order from least to greatest with no repeats. So this would be my domain for this relation, or I guess you could call it a function. And then my range would be all the y values in order with no repeat. So we have -2, -1. So that would be my domain and range. And as we said, we know that this graph is a function. So yes, function. And again, there were two ways that we looked at it. So there was no repeating x values, and it also passed the vertical line test. Okay, so let's get to the actual question. So the actual question said we wanted to find the inverse of a relation M and then graph the relation and its inverse in the same coordinate plane. So now if I want to find the inverse, oops. So the inverse table, in order to find this, if you recall from up above, to find the inverse of a relation from a table, you switch the x and the y values. So my inverse table, I take my x and y values from my original function and I switch them. So now my y values become my x values, and all my x values become my y values, and you want to keep those same points together. So remember, we're just switching the x and the y. Now that I have my inverse table, I can go ahead and graph these values. So I have -2, -1, -1, 0, -1, 1, and -2, 2. So these would be my inverse points. Now for these inverse points, notice that we have repeating x values. -2 has a y value of -1 and also 2. Because of that, I know that it's not going to be a function because it's not going to pass, again, the vertical line test. So if I take my vertical line again, notice that it hits here in 2 places. It also hits the green dots here in 2 places. So it's not a function because it doesn't pass the vertical line test and we have repeating x values. So the inverse is not a function. Another cool thing that we can talk about is the fact that inverses are always reflection across the line y equals x. So I'm going to write that down too. So, oops, inverses are reflections across line y equals x. So if I were to draw a line using a ruler on my graph, the line y equals x, I'm going to put my arrows on because it goes on forever. Notice that if I were to fold my graph on this line, that each of the points on either side would match up. So this point right here would match up with this point. This one matches up with this one. This one would match up with this one. And this point right here would match up with that point right there. So that's another way that I can tell that my graph is a reflection across the line y equals x, tells me that they're inverses of each other. So that's how you find the inverse from a table. Again, switch the x and y values, and then you can plot them. Now let's go ahead and find the inverse of y equals 3x minus 10 algebraically, which means by hand. So remember, as it was above on your paper, it says to find the inverse algebraically, switch the x and y values, and then you solve for y. So in this case, we have our y becomes x, our x becomes y, and now I'm going to solve for my y. So add the 10, and I get x plus 10, because those are not like terms, equals 3y. I need to solve for y by getting rid of that 3 by dividing it. So when I do, I get y equals x plus 10 over 3. You can also write this like y equals and separate these two as 1/3 x plus 10/3. Either way, it would be fine to do your equation. So I'm just going to leave it like this for now. So this is my inverse. Now, for this inverse, if we wanted to figure out whether or not this was a function, the way that I would do this is I would plug it into my calculator, and I would look to see, does it pass the vertical line test? So if I plug this into my y equals on my calculator, I have x plus 10 divided by 3, and I just wrote this equation over here. If I hit graph, notice the graph is just a line where my slope is my slope is 1/3 and my y-intercept is 10/3. And notice that if we were to graph this, even if I zoom standard window, it passes the vertical line test. Therefore, I know it's going to be a function. So we could write that this is a function, even though that wasn't the question. So it's nice that we have a graphing calculator in order to be able to help us with telling whether or not an inverse is a function. All right, so let's go to the next one. So the next example says we want to graph y equals x squared plus 1 and its inverse, and then state the domain and range. Now, if you look at this equation that we have right here, let's go ahead and first graph it. So remember, you can use your graphing calculator to help you get a table of values, or you can just do it by hand. So I have my x and my y. So I'm going to pick values that give me both negative and positive when I graph this. And remember, we can easily find the vertex by using negative b over 2a, which we learned earlier in the year, to find what the vertex is going to be. So if I do that, my b value, notice, is 0. So x equals negative b over 2a would give me my vertex. If my b is 0, negative 0 over 2, my a value is 1 because this is in front here. So I would get 0. So I know my vertex is going to be at 0. If I plug 0 into my equation, 0 squared plus 1 would be 1. So I have a vertex at 0, 1. So I want to pick points, remember, on either side of my vertex so that I can get my U-shaped graph, which is called a parabola. Since this is a quadratic equation, remember, it makes a U-shape. So for this, now, if I pick 1 and plug it in, 1 squared is 1 plus 1 would be 2. If I plug 2 in, 2 squared is 4 plus 1 would give me 5. And then if I keep on going, then I'm going to do the other side. So we have negative 1. Negative 1 squared is positive 1, plus 1 would be 2, and negative 2, if I plug that in, would also give me 5. So if I start plotting these points, I have 0, 1, and then 1, 2, negative 1, 2, and 2, 5. And it starts to show my parabola or U-shape for my graph. So that's my original equation. Now I want to graph its inverse. So remember, if I want to graph the inverse, I can take the table that I just made and I can switch my x and my y values. So if I switch my x and my y values, I have 5, 2, 1, 2, 5, negative 2, negative 1, 0, 1, 2. So when I graph this, I get 1, 0, and then I have 2, 1, and negative 1. Then I have 5, 2, and negative 2. And this would be the equation of my graph for the inverse. So I just drew in my line y equals x to show you that if you were to fold the graph in half on that line, that each of the graphs would be reflected to the other side. So you could think about folding your paper in half and looking at a light, and you should be able to match up the graphs. Now that would be to use the tables, or if I wanted to, I could find the inverse by switching my x and my y values and solving. So let's go ahead and also do that way. So I have then x equals y squared plus 1. So if I want to solve for y, I have to subtract the 1. So x minus 1 equals y squared. And then remember, in order to get y by itself, if it's squared, I have to take the square root to get rid of a power. And if it's an even power, I don't forget that you need your plus or minus in front. So y would be equal to plus or minus the square root of x minus 1. Now, if you wanted to graph this in your calculator, you would have to do both the plus and the minus separately because we don't have a plus or minus button in our calculator. So if I wanted to just go ahead and show you this graph, I would have to graph the square root of x minus 1. And then I would also have to graph the negative square root of x minus 1. And when I graph these, notice I get my parabola. Sorry, one's thicker because I have it thicker on my graph here. So if I go back here, and I also graph my other equation, which was x squared plus 1, my original equation, it's right here. So that's what our graph looks like, so we know we did it correctly. So now for this, if I look at the graph that's in red, the graph that's in red is a function. So this is a function because it passes the vertical line test. If you look at my graph that's in blue, this is not a function because it does not pass my vertical line test. Now, another thing that we're going to learn is there's another way to tell whether or not your inverse is going to be a function. And the way that you can tell whether or not your inverse is going to be a function is by using what we call the horizontal line test. So the horizontal line test is always used on your original graph to see if the inverse is a function. So if I look at my original graph, which was y equals x squared plus 1, notice that this does not pass the horizontal line test. Because it doesn't pass the horizontal line test, that tells me right away I know my inverse is not going to be a function. If you think about it, you're reflecting this over the line y equals x. So when I do that, this line ends up then changing to become a vertical line for this graph right here. So we'll talk about that more in just a second. All right, so again, recall, how do you tell if a relation is a function? If and only if for every input there is exactly one output, and from a graph we see if it passes the vertical line test. Now we also have inverse notation. Now this notation, notice it has the f and it looks like to the -1 power. That's not how we say it though. We call this f inverse is the way that that's read. So if f and f inverse are functions, they are called inverse functions. To determine if an inverse is a function from a graph, we can use the vertical line test, Or now we can use what I just showed you, which is the horizontal line test. If a horizontal line is drawn through the graph of f and intersects the graph in no more than 1 point, then the inverse of the graph of f is also a function. So just to, again, reiterate what I was talking about, the horizontal line test you use on the original graph to find if your inverse is going to be a function. So now if I do that for this problem here, if I look at my original function, h of x is equal to 8x minus 9, notice that this only hits in one spot as I move it up and down on my graph, and I could zoom my window out also to see that. And it's a line, so I know it's going to. So this passes the horizontal line test. And I'm just going to write HLT for horizontal line test. And so because this passes a horizontal line test, I know that, so this means the inverse is a function. If I want to tell if this graph right here is a function, I can use the vertical line test. Another way, again, you can see if it is a function is actually finding the inverse, graphing it, and then seeing if the inverse passes the vertical line test. We only use the horizontal line test on the original function. So now if I go to the next one over here, if this is my original equation that I have, notice right here, this hits in more than one spot all over my graph, so it hits there, and then if I moved my point here, then it would hit here, and it hits on both sides, on this side and that side. Because it's hitting in two places, I know that the inverse is not a function because it doesn't pass the horizontal line test. So if I were to graph my inverse equation would actually be something like this graph in red right here. It would be a sideways parabola. And notice that if we do the vertical line test on that sideways parabola, it would not pass. That's why we can tell that it would not be a function. Or again, as I said, horizontal line test is nice because just in case if you accidentally make a mistake when you're solving for your inverse, it's a nice way to make sure that you are correct that your inverse would not be a function. Okay, so then the next part says we want to find the inverse of each function below. Is the inverse a function? So I challenge you to pause the video and then unpause it, and we'll do these together. So remember, to find the inverse, you switch your x and your y values. Remember, f of x is just function notation for y. So this really says y equals negative 5x plus 7. So if I want to find the inverse, I need to switch the x and the y. So this would be x equals negative 5y plus 7. Take the 7 to the other side. So x minus 7 equals negative 5y. Divide both sides by negative 5, and I get y equals x minus 7 over negative 5. And remember, we can rewrite this as y equals negative 1/5 x plus 5 over, or 7 over 5. All I did was separate the fractions. Either way is fine. So this would be my inverse. Now, if I wanted to see if it was a function, I could graph that and see if it passes the vertical line test, which it would. So yes, this is a function. And if I look at my original graph, negative 5x plus 7, I know that's a line, and so that would pass a horizontal line test, so that's another way that I can tell that my inverse would be a function. So because this is a function, we can actually, instead of writing y, because we're given f of x, we can use our function notation. So my function notation would be to write f inverse of x equals. So now we can use that. For the next one, we're going to do the same thing. So switch your x and your y's. And when I do this, I take the 7 to the other side. And then I want to solve for y squared to take the square root of both sides. So y would be equal to plus or minus the square root of x minus 7. This is my inverse. If I were to graph x squared plus 7, my original function, that's a parabola, and a parabola is not going to pass the horizontal line test. So I know this inverse is not a function. I could also graph this graph here and I would see it's not a function. Another clue that tells me it's not a function is because notice that I have the plus or minus in front. That means I'm going to get two output values every time I have an x value, which tells me it's not a function. So from the last one, again, same thing. Switch my x and my y. So y equals the square root of x plus 1 and then minus 3. So now I need to switch. So this would be x equals the square root of y plus 1 minus 3. I want to get the radical by itself to isolate it so that I can solve for y. So add the 3 to the other side. And then I'm going to get rid of that radical by squaring both sides because it's an index of 2. So when I do that, I get x plus 3 equals y plus 1. And then the last step would be to subtract the 1. So I get y equals x plus 3 minus 1. And this should be squared. Now, it didn't tell me to put this in standard form, so I can leave my answer like this. If it said to put it in standard form, I would have to FOIL or box x plus 3 out and then subtract the 1 from it, which would be fine. You can do that, but it's more work than we have to do. So if I were to graph this equation, this right here in my calculator, I know it's going to pass the horizontal line test. This passes the vertical line test, so I know that, yes, this is going to be a function. So yes, function. And again, just plug it into your calculator to look. Now, one thing that I forgot to do over here is I wanted to talk about the domain and the range of the equation since we did that in the last section. Now, remember, we have our domain restrictions. The domain restrictions is you look for variables in your denominator, and you also look for variables under radicals. So if you look at the graph that's in red, I know that my domain is going to be all real numbers because I don't have any variables in my denominator or underneath the radical. So remember, that's the symbol for all real numbers. And my range for this graph, notice that my y values are starting here. So my range, that means, is starting at 1 and it's going all the way up to infinity. So I have y values that are greater than or equal to 1 in this case. Now let's do our inverse graph. So for my inverse graph, my domain, if you look at your x values, well, my domain's not all real numbers because look where your x values start. Your x values are starting here at 1. And also remember that our inverse equation had a radical in it. So because of this right here, that's how I know I'm not going to have all real numbers for my equation because I could get a negative underneath my radical. So what I do to find it is I can take x minus 1 and I set it equal to 0 and I get x is equal to 1. That tells me where I'm starting on my graph. So if I look here, I know that my x values are starting at 1 and they're going all the way to infinity. So I know that 1 is less than or equal to x. So I have x values greater than or equal to 1 if you want to write. So that's my domain. And then my range values, I can keep going on and on forever. It's keep going up and down here. So my range in this case is going to be all real numbers. And another way that you can find that is, remember, when you're doing your inverse, you're switching your x and your y's. So if your domain right here is all real numbers and you switch them, that means your range would be all real numbers here. And if your range is numbers greater than or equal to 1, well then over here, instead of y being greater or equal to 1, it becomes x greater or equal to 1 because we switched our x and our y values. So that's pretty cool. All right, so we'll go back over here. Now, the last part of this is to determine if two equations are inverses algebraically. Now, in order to do this, you have to use composition of functions. And composition of functions, remember, is when you do f of g of x or g of f of x. Now, in order to determine or verify if they are functions, you have to do all 3 of these steps. So to verify inverses, you must show all 3 steps that we have right here. So for example, it says determine whether each pair of functions are inverses. Now, I can't just switch the x and the y's and show that they are. I have to use this proof. Now, if you look at this proof, why does it say right here f of g of x equals x and g of f of x equals x? Because when you're doing the composition of an inverse, you're basically undoing what you did before. And the reason you get equals to x is because if you have y equals x, remember that was the line of reflection. So basically you're undoing what you did from the first function and you're getting your line of reflection, just your x value out. That's why they would be inverses. So for the first step, I need to show that f of g of x must be equal to x. So remember, my inner function is g of x, and that means I'm taking g of x, which is this right here, and I'm plugging it into x for this equation. So this would be equal to, and I'm taking x plus 5 and plugging it into my equation. So when I simplify this, I get x plus 5 minus 5, which is just equal to x, so that one checks out. Now I need to do my second step. For my second step, now I'm going to take my equation and do g of f of x. So now I'm taking this f of x equation and plugging it in for x into g of x. And when I do that, I get x minus 5 plus 5, which is equal to x. And then the last statement that we would want to write is since f of g of x equals g of f of x, therefore, and they both equal x, therefore they are inverses. Which is pretty cool. So again, we can't just switch the x and the y's on this one because we're trying to show that they're inverses by using this these three steps that we have. So what I would do for you guys is I want you to do B on your own. So you guys do this for class. So verify whether or not f of x equals 3x minus 2 and g of x equals x minus 2 divided by 3 are inverses using the 3 steps. And then we'll talk about this in class and do some more of these problems.